Welcome back, and welcome to a new unit, Unit 5. I've got good news and bad news. If you struggled with the last unit, the good news is this unit is not strictly about probability. The bad news is there are still probability concepts involved. So I hope that starting with this unit, we're really kind of moving away from very strict definitions of things, and we're getting into a bigger, wider world of trying to explain something about populations based on samples. And I know we've been talking about that a little bit so far, but this is the unit where we really start putting everything together. This is like the transition unit that connects everything that we've talked about so far. So you know all the terminology, you've got some probability now under your belt, and it connects all that to what we're going to see starting in the next unit all the way to the end, where we're really talking big picture stuff. This is the transition unit. So this is what's keeping it all together. So let's start with this example here. Mr. Binkard has been teaching trig for about 1,000 years. I have that on good authority. He's actually, he's a demigod. He's been around for a long time. Mr. Jones just started teaching trig this year. So let's say we take a sample, a random sample of students from each of those two teachers, and we calculate the average grade, the average trig grade for both of those teachers. We find that the average grade from Mr. Binkard's class is an 83%, and the average grade for Mr. Jones's class is a 76%. So based on those results, does this prove that Mr. Binkard is a better teacher? Or maybe he's just an easier grader? Can we use these results to make those claims? I would hope that your first response to that is no, because we didn't perform an experiment, so we can't make a cause and effect relationship. If so, fantastic. I hope you also picked up on the fact that this was actually fairly well designed for a sample survey, because the sample was taken randomly. It could have been worse. We could have just taken volunteers, or something like that, right? But the fact that this wasn't an experiment, maybe we can't answer these questions directly, but you see what we're trying to get at. We want to be able to use this data to say something about these two teachers. Can we say anything based on these results? Well, I've got some questions. Would we get these same results if we took random samples, again, different random samples from each teacher? So let's say we took 10 trig students from each teacher and we got this. If we took different samples of size 10, would we get these same results? It's possible, I suppose, but that's probably unlikely, right? These grades might be a little different. They might be very different. Who knows? Maybe the samples we took the first time were just unusual, right? Maybe in reality, Mr. Jones's student's average grade is higher, but just because of this sample, it was lower. How much does this reflect the actual population? We don't know if we just take one sample. If we take more, we're probably going to get different results, so that might cast doubt on this. But let's say we just kept taking random samples of 10 students at a time, over and over and over and over and over again. We might then start to see some kind of pattern in the results. Maybe Mr. Binkard's average grade tends to hover around this 83%, and Mr. Jones's average grade tends to hover around this 76%. We could be able to say something about that. Maybe not necessarily a cause and effect relationship, but we might be able to use data like this if we take many more samples and be able to say something about that. And that's what this unit is going to be about. It's about the power of taking lots of samples from the same population and seeing what that might tell us. We can take one sample, and that's fine. But if we think about what happens when we take many samples, we can start to say a lot more interesting things. And it makes it easier to take a sample and see if it reflects the entire population. We can say some more stuff about that. All right, I'm not pulling any punches in this video. I'm starting out with just peppering you with questions. And this one's kind of mean because we just got done with a unit where we were dealing with a bunch of discrete random variables, but we're going back to this one. What does it mean for a variable to follow a normal distribution? Well, I kind of gave you a hint in the very first one. It has to be a continuous quantitative random variable. Any variable that we were just talking about in the last unit that's geometric or binomial, those are discrete. That's not going to fly with normal. These have to be continuous. Remember the bell curve? The variable you're looking at, the random variable, has to be able to take on any value under that curve. So only continuous quantitative variables are allowed. So getting even more specific than the fact that it's continuous and quantitative, I kind of already said that. That bell-shaped curve, that's classic normal distribution. So you've got this curve. And if you were asked to describe the shape of this curve, what could you say about it? It's unimodal. It has a single mode right in the middle. And it's also symmetric right down the middle. Pretty much following the order of how we learned about the normal distribution, this pretty much came first. And then we're like, okay, so the mean is in the middle, right? And we established the middle first, and then we're like, okay, how spread out are the data values? We introduced the idea of the standard deviation in terms of the 68, 95, 99.7%, or empirical rule. This rule, all of these things, only apply to variables that follow a normal distribution. I don't want you to think that this is always the case no matter what. But remember, the empirical rule said 68%, approximately 68% of all data values from a population that is normal in shape fall within one standard deviation of the mean, anywhere from a standard deviation below to a standard deviation above the mean. If you go out 2 standard deviations on each side, you're getting approximately 95% of all population values. And if you go out a 3rd standard deviation on each side, you're getting 99.7% approximately of all those population values. Very, very few values are more than 3 standard deviations from the mean on either side. We know that any variable that follows this normal distribution, it has some mean and some standard deviation. We know we can calculate z-scores using this formula to standardize to the standard normal distribution. Right, so if we have some normal distribution, and we'll get into an example in a little bit, as long as we know the mean and the standard deviation, then for any value for that variable, we can calculate the z-score, and that tells us how many standard deviations above or below the mean that value is. And the nice thing about the standard normal distribution, you can take any normal distribution, any mean, any standard deviation, and compare them apples to apples, as long as you standardize values from both of them, or any of them. Right? And also, the z-scores, once you calculate these, allow you to do more things. Once you've calculated a z-score for a particular value, we could then use normal CDF to find the areas either to the left of a value, to the right of a value, or if we have 2 values, the area in between. So we can make statements like 64% of all values fall between this value and this value. And remember, this was the first distribution we learned about to use on the calculator. I know for binomial and geometric, we can use PDF or CDF. For normal, we only ever use CDF. We never use normal PDF. Remember that. If you were to use normal PDF, what you're measuring is not the area under the curve, but how high the curve is at that x value. That's never what you want. Okay, so we can always use normal CDF to find those areas. And just one more thing, because I'm running out of room on this column, we can also, kind of like normal CDF, we can do the reverse operation. And if we know a certain area to the left of a value, to the right of a value, or between two values, we can use the inverse norm function on the calculator to take those areas and figure out which z-scores fit them. So if we knew that some variable followed a normal distribution and we wanted the z-score that represents 30% of values are less than it, we could put in inverse norm of 0.3 to the left, and that would spit out the z-score that we needed. Pretty simple stuff. So I just wanted to remind you of all the things we can do for normal random variables, because we took some time away to talk about discrete random variables. But I want to make sure that we get back into normal mode, because a lot of the things we're going to talk about in this unit that allow us to answer questions like this actually involve continuous quantitative variables. And the most common model we're going to be using, at least at this point, for variables like that is the normal model. The rest of this video is going to be devoted to going through a series of questions based on this setup, just to get us back into the normal mode. So the distribution of heights of young women aged 18 to 24 is approximately normal, with a mean of 64.5 inches and a standard deviation of 2.5 inches. So our first question here, part A, what is the probability that a randomly selected woman is taller than 68 inches? So, see if you can tackle that one. For each of these parts, it would be best if you pause the video, try working on it yourself, and come back only when you have it, or if you're stuck to the point that you can't go any further. Go ahead and give it a shot. At least for the first part here, I'm going to go through it, not necessarily step by step, but I'll show you a little bit of the process, just because it's been a while. So you're looking for the probability that the random variable is greater than 68. I didn't define the random variable. I probably should have. X is the height of a random young woman. So we want the probability that that is greater than 68 to answer this question. But we can't answer this until we standardize and find the z-score. So we use the z-score formula. We plug in 68 for x. The mean is 64.5. The standard deviation is 2.5. And that gives us 1.4. So what we want here, this means the same thing. But now that we know the z-score that we're interested in, we can use the calculator. However, at this point, before I start using normal CDF, I like drawing a picture of what this looks like. I know it's been a while since we've done problems like this, and you might be like, okay, I know, once I've got the z-score, I can use normal CDF, I know how to get the answer. That's great. But I want you to be able to make sense of what it is you're looking at here, because a lot of students forget that they should sketch what they're doing, and they end up getting answers that don't make sense, and if they had drawn the sketch, they would realize that. So this is like a fail-safe. It also shows whoever's grading your test that you know what you're doing. So once you have the z-score, the mean of that distribution is now 0, and you're interested in 1.4, and we want the area to the right, so we're going to shade over here. So before even using the calculator, I know I'm looking for an answer that's less than 0.5. This is definitely less than half of the total area under the curve. So I know that this is normal CDF, and I'll be honest, I forget the arguments. So I'll bring up my calculator. Yay. Second distor, normal CDF. What is it I need? All right. Lower, upper. So lower here is the lowest z-score we're interested in. It starts at 1.4. The upper is the highest z-score we're interested in. That goes up to infinity, but something like 9999 should be enough. It wants the mean, which, since we standardized and found the z-score, the mean of this distribution is 0. And the standard deviation of the standard normal distribution is 1. So we just need to put those in. Lower is 1.4. Upper is 9999. Mean of 0, standard deviation of 1. We get 0.0808 if we round up. Yeah. It's convention to round probabilities like this to 4 decimal places, because some of those old boomer college professors, they don't use a TI-84 to calculate these areas. They use tables of values, and those tables report these areas to 4 decimal places. So you should too. And this is 0.0808. If it said to interpret your answer, all you'd have to say is the probability that a randomly selected woman is taller than 68 inches is 8.08%. All right, next question. What is the probability that a randomly selected woman is shorter than 66 inches? This is another reminder, we always use normal CDF, because when we're talking about a normal random variable, you're never going to be asked what's the probability that a randomly selected woman is exactly 66 inches tall, because that probability would be 0. Assuming you had an infinitely precise measuring tool, no one would be exactly 66 inches tall. So we're only ever going to be asking questions like taller than, greater than, shorter than, less than, or between 2 values. So that's just another reason we always use normal CDF. So go ahead and tackle part B. Okay, I'm most of the way to the answer for part B. We want the probability that x is less than 66 now. Shorter than is less than. Calculate the z-score, you get 0.6. So we want the probability that z is less than 0.6. I've drawn that here. We're looking for all the area to the left of 0.6. So this is what we need to type into normal CDF. Lower is negative 9999 because we're going all the way to the left. The upper is now the one that we want here is 0.6. Goes up to that value. Mean is 0, standard deviation is 1. For the calculator though, to type in negative 9999, make sure you're using the negative key here. If you use the minus key, you're going to get an error, and it hates that. And we've talked about that before, but it's been a while, so I just want to make sure I put that in there. Negative 9999.601. Enter. I get 0.7257. Looks good to me. 0.7257. So the probability that a randomly selected woman is shorter than 66 inches is about 72.57%. Part C. Between which heights are the middle 60% of young women? This is obviously a different question. It doesn't have the word probability in there because we already have the probability part of the question. We actually want the heights themselves. The x values are what we're looking for. So for students that don't like drawing these normal curves, they have trouble even knowing where to start on problems like this, because that's exactly what I would do at the very beginning. And even for the problems we've already done, you could draw a normal curve at the very beginning that represents the original distribution. I just tend to only draw it after I've standardized. That way I don't get confused with what the mean is and what the x values versus the z-scores are. I always do it in terms of z. But here, right from the very beginning, I'm drawing that curve just to visualize what this looks like. Okay, so this is the original curve. This is not z-scores. And we know the mean here is 64.5. And we want the middle 60%. The middle 60%. So I'm just going to estimate here. I did a bad job making it symmetric, but don't worry, it's not necessarily to scale. Okay. So the point is we want to know what these x values are that represent the two heights that we need. And all we know is that this is 60%. Well, is there anything else that we can figure out based on the fact we know this is 60%? We should be able to know what these two pieces are as well. We know that the normal curve is symmetric about the mean, or at least it should be. Maybe it's not in your drawing, but close enough. So of the 40% left over, it has to be split half and half. This has to be 20%, and so does this. So, to find this value, you could use not normal CDF. That's for when you've got the value and you need the percentage. If you've got the percentage and you want the x value, you're looking for inverse norm. So what is it we need to use inverse norm? It's still under second dister. It's number 3. Okay. If you've got an older school calculator and all it says is inverse norm, you're not going to have all the options it says here, but I'm going to explain it in a way that you could do it on your calculator as well. So for area, for this type of calculator, you could put the area to the left, the center, or the right. If you've got an older calculator, you need to give it the area to the left. It won't accept anything else. Well, it won't know that that's something else. It will always assume it's the area to the left. So if you're looking for this value here that has 20% to the left, you need to put 0.2 here. Okay. And I don't remember when I first taught this in chapter 5, but you don't need to go through the z-scores using inverse norm. You can actually plug in the mean and standard deviation of the distribution as it is. You don't even have to go through z-scores. So, sorry, I'm going to be writing what you need to write here. So, area equals 0.2. It wants the mean and standard deviation. The mean is not 0. The mean of this distribution is 64.5. And the standard deviation is 2.5. Okay, so 0.2, 64.5, and 2.5. Now, where this calculator says area left center or tail left center right, I'm always going to use left there because I didn't grow up with a calculator that had the option. But you'll see in a second where it might come in handy. I'm always going to use the area to the left, which is 20%. So I'm always going to use tail left. If you just leave it like that when you're writing out your work, they'll assume that that's what you're using, is the area to the left. They'll understand that. So tail left, enter. It gives you 62.40. And that's in inches, just so we have some context there. And is that reasonable? Well, this number is this one. It's less than 64.5. So sure, that seems reasonable. Now let's find x2. This is where, if you've got a fancy calculator like this one that shows that window, you've got options. If you use, let's go to inverse norm real quick. If you use tail right, which you have the option of doing, we're looking at this value now, that's 0.2 to the right. So you could leave the area as 0.2, but if you check area to the right, it's going to give you what this number is. If you've got an older school calculator and you have to give the area to the left, you can still do that. You just need to know how much of the area is to the left of this value. Luckily, you've got that written here. You just take this area and add them together. That's going to be 80%, or 0.8. Okay, so I'm going to change the area to 0.8 here and keep the tail to the left. I get 66.60. But I also want to show you, if you do use the area to the right and make it 0.8 or 0.2 and use that, we should get the same answer. Exactly the same. Okay. My only thing is, if you're going to use tail right, you need to write that here so they know that you use the area to the right. Otherwise, they'll assume that you were looking at 0.2 to the left, and they'll wonder why they're not the same. Okay, so those are your two values. The middle 60% of young women are between 62.4 inches and 66.6 inches tall. One part to go. Hopefully you wrote down the original distribution, because now it's obscured by the calculator. The shortest 2% of women are shorter than what height? I want to see if you can tackle this one on your own, based on the parts that we've already done. Take a second, pause the video, come back when you've got it. I was just about to hit enter on my calculator to get the answer, but I want to make sure we set things up correctly. The shortest 2% of women, so this is another one where we have the percentage and we want the X value. I'm going straight to a picture first, drawing that normal curve, putting the mean in the middle. The shortest 2% of women are the ones furthest to the left. So this is 2% is less than whatever the X value is going to be. So again, this is an inverse norm problem, not normal CDF. Remember, normal CDF is for when you want the area and you have this value. Maybe you've calculated a z-score already and you want the area. That's normal CDF. It essentially does integration for you, if you know what that is from calculus. Normal CDF takes integrals. Inverse norm takes the area, the percentage, and gives you the X or Z value that you want. So we want 2% of the area to the left. If you got the same answer that you did for this one here, it's because you typed in 0.2 here for 2%. 2% is 0.02. That is the most common mistake that I see on any percentage that is less than 10. People don't put it in the right decimal, and that's why they get it wrong, and it's so silly. But just make sure you're extra careful typing that in. 2%, 0.02. Same mean, same standard deviation. Type it in. Boop, boop. We get 59.37. Yes, 59.37 inches. So these problems, I just wanted to get you back into using the normal model. Right? You can calculate z-scores. You can draw your curves. You can use normal CDF or inverse norm to answer all these types of questions. We're going back through this material because what we're about to talk about is going to build on this concept. And we're going to be talking about taking lots of different samples at the same time. So it's important to have this foundation so that we can build upon it, so it doesn't all come tumbling down like a card tower. House of cards. There it is. I don't want your knowledge to fall apart like a house of cards. So we're rebuilding that foundation, making sure it's nice and sturdy. So I hope you're ready for the rest of this unit. I know I am. I wonder what's coming around the corner. Who knows? Tune in to find out. We'll see you next time.